This lesson's on momentum and impulse. Here are your objectives. So we're actually specifically talking about linear momentum here. And linear momentum is the product of an object's mass and its velocity. And so it's given by this formula. Linear momentum, which we give the symbol p with a vector arrow over top, is equal to mass times velocity. And because we're multiplying a scalar, mass, by a vector, velocity, we get another vector. So linear momentum is itself a vector, and it keeps the direction of the velocity. So it's a vector with the same direction as the velocity. And its units are kilograms, coming from the mass here, times meters per second, coming from the velocity here. So units of linear momentum, kilogram meters per second. And we use the term momentum in physics very similarly to how we use it in everyday life. If we were to think about a truck moving at 10 meters per second or a truck moving at 3 meters per second, the truck moving at 10 meters per second has more momentum because it has greater velocity. And if we think of a truck moving at 3 meters per second compared to a mosquito moving at 3 meters per second, the truck moving at 3 meters per second has more momentum because it has a greater mass. Once again, just a reminder that momentum is a vector. So this ball moving at 5 meters per second to the right and the identical ball moving at 5 meters per second to the left have different momenta because the velocity is in different directions. And that's going to become important when we start to think about the relationship between momentum and force. So let's actually start to look at that relationship between momentum and force now. It turns out that Newton actually stated his second law in terms of momentum, although we're used to thinking of Newton's second law as being this, F net is equal to ma. Newton stated it like this, that the net force acting on an object is the time rate of change of its momentum. That's what this is showing here, delta p over delta t. Now if you think of our definition of momentum, p, delta p would be equal to delta mass times velocity. And if the mass is staying constant, we can bring that out front and we get mass times the change in velocity over the change in time. Well, this, of course, is just acceleration, and so that's where we get mass times acceleration. But Newton, again, first stated his second law in terms of momentum, where net force is equal to the time rate of change of momentum. Now, we can rearrange that to give us this relationship, that F net times the elapsed time gives us the change in momentum. And this product, F net delta t, is given the term impulse, and that has the symbol J like this. So rearranging this, we get F net delta t is equal to delta p. In other words, to change the momentum of an object, you need to exert a force, and you need to do that over an interval of time. If you increase the force or increase the time over which you apply that force, you get a greater change in momentum. And if the mass is staying the same, you're going to see a greater change in the velocity, therefore. Once again, the product of F net times the time over which that force acts is called the impulse of the force. And if you think of the units of F net, which are newtons, and delta t, which is seconds, then it becomes clear that the units of impulse are Newton seconds. But remember that newtons themselves are equal to kilograms times meters per second squared. You can get that from F net is equal to ma. Therefore, multiplying kilogram meter per second squared by seconds gives us just kilogram meters per second. And that was our units of momentum and therefore of change in momentum. So you can see that everything works out. Let's do an example. Imagine that you have a constant force of 5 newtons left acting for 2 seconds on a 4 kilogram object that started off moving with a speed of 3 meters per second right. We're asked to find the object's velocity after that time. Well, we know that the change in momentum, which is equal to the final minus the initial momentum, is equal to the impulse of the force, or F net times delta t. Rearranging this, we can solve for the final momentum. It's going to be equal to the initial momentum plus the impulse. Now, replacing the symbol p with mv, we have mv2 is equal to mv1 plus fnet delta t. And because we're solving for the velocity, v2 is equal to the whole right side divided by the mass. Now let's use right as the positive direction, and we can plug everything in. So we get 4 kilograms multiplied by plus 3.0 meters per second, plus our net force, which was negative 5 newtons, because it's to the left, multiplied by 2 seconds, and that's going to be divided by our 4 kilogram mass. And when we work that out, 12 minus 10 is 2 divided by 4 gives us a final velocity of positive 0.5 meters per second. Now in that example, we were finding the impulse of a constant force. When the force is changing, we can't simply apply this formula. Rather, we need to take an approach like we did when we looked at the work done by a changing force. If you recall, the work done by a changing force was equal to the area under a force position graph. Here, we're going to take the area under a force versus time graph, and that's going to give us the change in momentum. Let's look at an example. Here's our force versus time graph, and we're told that this is showing the force on a 2 kilogram box that starts from rest. And we're asked to find the final momentum of the box at time is equal to 6 seconds. Well, again, the change in momentum, or the impulse, is equal to the area under this force time graph. So because it's a triangle, it's equal to 1/2 times 6 newtons, which is the height, times 6 seconds, which is the base, which gives us 18 Newton seconds. That's our impulse, or our change in momentum. Well, the final momentum is, in this case, because the change in momentum is equal to p2 minus p1, and the initial momentum is 0, the object started from rest, then p2 is just equal to the change in momentum, which we just found is equal to 18 Newton seconds, or if we want to put it in the familiar units for momentum, 18 kilogram meters per second. Those are equivalent. So again, we found the change in momentum from the area under a force time graph. Now if we want to find its speed, we can solve for velocity. Its velocity is going to be equal to its momentum divided by its mass. This is just a rearrangement of the formula we saw earlier. And so that's going to be equal to 18 kilograms times meters per second divided by 2 kilograms. And therefore we get a velocity of positive 9 meters per second, or a speed of 9 meters per second. So that's an example of finding the impulse of a changing force using the area under a force-time graph. Let's close by looking at some real-world applications of this impulse-momentum relationship. Again, remember that what we're talking about when we say the impulse-momentum relationship is that F net times delta t is equal to the change in momentum. The force, net force times the time over which it's applied, gives us the change in momentum. So airbags work by increasing the amount of time over which momentum is changing. When you're being brought to rest by an airbag, we can't alter the change in momentum that needs to happen, because you need to be brought to a momentum of 0 from whatever momentum you had before. So the change in momentum is fixed. But by increasing the amount of time over which that momentum change happens, we can decrease the net force that needs to be applied. And because it's that net force that's damaging to us, by increasing the time and decreasing the force, we can protect ourselves. So airbags are an application of this impulse-momentum relationship. Another application is following through on a swing, let's say a golf swing or a tennis swing. In that case, the force that you apply might be relatively fixed. But by increasing the amount of time over which you apply that force, you can increase the change in momentum that you give to the ball, therefore the change in velocity. So airbags and swing follow-throughs are two different examples of impulse-momentum relationship.